All right, so I love the name of the session, where do blah comes from. Or I guess it's did, but I changed to do because they still come in. So where do ultra-high energy cosmic rays come from? But before I talk about that, let's, congratulations to KIPAC. You guys did a great job. It's really exciting to be here, celebrating the 10-year anniversary, and we are wishing many, many more decades to come. So I tend to talk for too long, so my friend here will have to shut me off very quickly. So I thought I'll give you the bottom line, and here's the bottom line. Okay. Got one joke in, I can now go and do serious work, right? So here's the obvious first place we start, the cosmic ray spectrum. And we have, usually multiplied by something, in this case 2.5, the energy times 2.5. Then you can see the knee, the ankle, and some turnaround. For the high energy physicist, this is where LHC is, right there. So we have a lot more going on than the LHC. And that's kind of fun, and that's what we would love to start using. Unfortunately, we can't control the beam, and we don't even know what the accelerator is. The accelerator certainly is stronger than the LHC. It has to either have a radius of 10 to the 7 kilometers or a 10 gigatesla field, and that's magnets, if you want to use the same ring. So that's the same discussion as what we call the Hillis plot, and this is where astrophysicists would plot objects which can populate lots of spaces in this R versus B plot. There's a lot of objects over here. There are very few that reach a containment of a proton at 10 to the 20. That's this blue line, and it's a little bit easier for iron at 10 to the 20 to be contained. That's just a first requirement. We then want to accelerate it, and usually these things are relativistic, so things get very hard. Now, protons are much more abundant, but they're harder to reach 10 to the 20. Iron are easier to accelerate, but they're not, expected to be the most abundant part of the story, but then we have found differently recently. Accelerator efficiencies are much less than 1, or 100%, so this is just the minimum requirement. And the fact that this region over here is empty is the big question. So if you look at possibilities, people have looked at large shocks in intergalactic medium. It's very hard to do that in these objects, but people are trying. AGN, there are many options in the AGN, hotspots, jets, and AGN nuclei, and the gamma ray bursts. It's all very difficult, and usually it involves some transients. And here, we're going to hear after me, Kei Feng talk about neutron stars as an option, and John Ahrens is here too. We've both worried about that option. No, that's not the point here. The point here is to talk. Okay, so just for those who didn't hear the definition yet, ultra-high energy cosmic rays is above 10 to the 18, in my definition at least, and that's 1 eV, and so this is the region we would be focusing on. Somewhere in that region, there will become a transition to extragalactic. Maybe it's a bit earlier than that. Maybe it's a little bit later. The ankle is sort of a natural place that you could imagine something coming up when something else is coming down, but people have argued that might be a second knee, and this is an ongoing discussion. But certainly we know that it is extragalactic past 10 to the 19, independent of what it is. Even if for iron at 10 to the 19, it should be extragalactic. Above 20 eV, we should have extragalactic iron. And for protons is around 1 eV. So, this region here is certainly one, depending on the composition, thought to be extragalactic. So, and how do I know that? We know that by playing with huge variances on models that can fit the galactic magnetic field. So this is a magnetic field of the galaxy ranging from 2 microgauss to 8 with scale heights from 2 kiloparsecs to 8 kiloparsecs. And then Auger has given us a limit on the anisotropy towards the galactic plane, for example. So we would see the galactic plane, and here are solutions for a proton. So a proton would be in black here. So this is the anisotropy from the galactic plane for a proton source at these energies. So this is 10 eV. And you see that it's way higher than the limit. So that means you can't do that. You can't put protons in the galactic plane and not see some anisotropy. For iron, which is in red, you can delay. You can sort of reach the upper end of this story up to about 20 eV. So, it's pretty safe to say that above 20 eV, it's extragalactic, probably earlier than that. And then, as Justin already mentioned, the GZK cutoff is what we think is going on here. Maybe it is the maximum energy of an accelerator. and I'll get into that for a second. So let's remind ourselves what the GZK cutoff is. Greisen, Zatsepin, and Kuzmin, those three gentlemen in 1966, talked about the end of a cosmologically meaningful termination of the cosmic ray spectrum, because protons reacting with the microwave background will give you, through the delta resonance, some pion production, and that will limit the energy of the proton you observe on Earth if it's coming from extragalactic sources. Here's what you can calculate for the proton energy loss length versus energy, and this is the GZK wall over here, and say, let's look at energy loss length in the solid black line. This is in blue, it's basically the adiabatic expansion of the universe, so you see the whole universe at 10 to the 18, 10 to the 17, if these are extragalactic, obviously. You can see most of the universe at 10 to the 19. You start having E plus E minus losses, but then at 10 to the 20, 10 to the 21, you see 10 to 100 megaparsecs. Okay, so that's going to change any spectrum. So here's a modification factor of a given spectrum of the cosmic rays. If you have a source at redshift 0.003, nothing will happen to the injection spectrum. Assume it's a power law, it will be the power law that it got injected, plus a little feature when you get to 10 to the 20. So the particles that were at 10 to the 21 will lose energy to 10 to the 20 and make a little bump. So you get a bump and back some sort of recovery. As you move your source to higher redshift, this effect moves to lower energies because the microwave background gets blue shifted. And so you get a bigger effect, and that gives you, so if you have a source distribution which has sources all over, different redshifts, you get an overall envelope to whatever power law you got in, and you might have a recovery if your accelerator keeps on going beyond 10 to the 21. So one of the beautiful things that one can see from the last decade coming out is this gorgeous spectrum. This is from 130,000 events of the Auger Observatory that was just shown at the ICRC in July. And these numbers are the number of events per bin. So we know this shape pretty well. This ANCO is very clear. And then you get to 90 events, 45, 7, 3, 2, no 2, 1, and upper limits. Okay, so the reality is that there is certainly a drop, so that's totally consistent with the GZK cutoff, and then basically your detector is not big enough to know exactly the shape. But for most of this energy range, we have a really beautiful precision spectrum. This is the Auger Observatory. It's a collaboration of over 500 scientists, 19 countries. Here's an actual shower. So what we're talking about is particles of extremely high energies which interact in the atmosphere. They produce a cascade of hundreds of billions of particles coming down, and this pancake of particles is measured by different detectors on the ground. In the case of the Auger Observatory, it is a water tank, that each of these little white dots is a water tank. And the distance between it is about a mile, it's 1.5 kilometers, and this is, the color scheme here is the, intense ones in red and so on. So you get the footprint of that signal on the ground. You also get fluorescence from this shower development from the electromagnetic part of the cascade will excite nitrogen molecules in the atmosphere, and that will give you a way to see the same shower if it's at night and dark. These are the fluorescence telescopes, which look at the same shower 10% of the time. So you get, in this case, 4 of these fluorescence telescopes seeing the same event, and that's how you get great precision for the whole shower development. So the current situation for this field is 2 observatories, the Pierre Auger Observatory with 3,000 square kilometers in Argentina, and the telescope array with 700 kilometers in the US, in Utah. This is what telescope array looks like. Instead of water Cherenkov tanks, they have scintillators, 510 of them over this region in Utah, and they're a little bit smaller than Auger, but the 2 telescopes give you a whole coverage of the sky, because you have the southern and the northern sites. And together, they agree very well in terms of the spectrum. Here's the spectrum. In 2012 at CERN, everybody got together and tried to do what's called a working group for the spectrum, and the working group is between all the different experiments. The leading ones, as I mentioned, is Auger and telescope array. Previously, AGASA was what, AGASA and high-res became telescope array. There's also Yakutsk, and when you put it all together, you see this very nice feature. The only trick here is that you have a 10% energy rescaling between telescope, well, 10% towards the mean, so it's actually 20% Auger to telescope array. But since the ICRC, actually, the Auger energy scale has moved 10%, so now it's 10% between the two, okay, if you are more interested in that energy. So the differential energies are easy. The overall energy scale is the hard part, which is when you have to really know the fluorescence yield in the air. So here's the current status. We have agreement on the shape of the spectrum. The energy scale is 10% difference between Auger and TA. And then we have a composition controversy. That's kind of fun. So how do we look at composition? We look at the shower development in the atmosphere. If it is iron, it will peak early and it will not fluctuate as much. If it's proton, it will peak deeper and it will fluctuate more. If it's photons, the peak is on the ground in the case of Auger, so it's very easy to tell. And neutrinos, they can do all kinds of things. So here's the prediction. So this is the data of the maximum of the shower. So there are two things one can do, is measure the average maximum of the shower or the width, the distribution, the variance between different maxima. So here is in Auger and here telescope array, the data in black, and here's what you expect for iron. And you see there is a spread between APUS, GS jet, and Sybil. And APUS, which is the solid line, has been the most studied in the LHC. So there's a huge overlap here between our community and the LHC forward physics people who are testing these models very well. And with the new LHC data, you see that the solid line is even further from the black dot, the black data, than the other kinds of models. So it does look like, it's heavy to begin with, but if you forget that there is a problem here that we don't really know exactly what the hadronic models look like, there is certainly a change in slope. So there is something happening here that changes into something else, and that means a change in composition. In the case of the telescope array, they don't have yet as much statistics as Auger, and they don't quite see a change of slope. I mean, it's consistent between the two, but there is also a difference between the ways the data is actually reconstructed. So one is in the atmosphere, the other is in the detector, and there's a lot of discussion. There's a working group that hopefully will find some solution between the two. Now, if you take the Auger data and you translate that into a average log A, meaning what kind of particles are we talking about? Depending on which package you use, what hadronic interaction model you use, you're going to get different results, but the trend is the same. So there's certainly a change in composition that you see in all of these. For the case of APUS, for example, it's a heavier, so even when you get to the lowest point, it's not all protons, and you get to heavier composition. Sybil and QGS jet are consistent with having proton-rich up to some energy scale, but then eventually it goes away. So how do we put this whole thing together? When you put this whole thing together, you get, I'm looking at the wrong number, so I have to speed up. You get, the spectrum here can be fit by different assumptions. In black, the assumptions are all protons. In blue and pink, the assumption is either iron or a mixed composition. And the way you do the mixed composition is actually by having many peaks of each different Z. So basically, this is where the question Justin was asking, is this really the GZK cutoff? For protons, it's definitely the GZK cutoff. But for a mixed composition, what you're actually doing is fine-tuning the maximum energy of protons to be low, and therefore the iron maximum energy is just where the gene thing, which is a bit uncomfortable, but that's what this kind of data is forcing us to do. Okay? And we'll hear more about this from K next, one model that does that. Now, one little coincidence to keep track of is that iron and protons have similar behaviors in GZK space, meaning the following, that if you have protons of 100 eV, 60 eV, and 40 eV, the distance that on average they can come from varies from hundreds of megaparsecs to tens of megaparsecs. For iron, it's actually the same. So iron at 60 and proton at 60, they have the same kind of behavior, and that's a coincidence because one is making pions and the other is being photodissociated. While anybody else, CNO and helium, gets really killed very early on. By 60 eV, they really only come from a few megaparsecs. So, there's this real selection. All right. So the current status is that we have this composition controversy, and clearly we need to get the anisotropies, because the anisotropies are going to tell us what is really the source. So there are hints above 60 eV, but there's no greater than 3 sigma signal. So I'm going to skip this part, but just tell you one thing. So remember this plot that I explained calmly. Here's roughly what you get: gigaparsecs, 100 megaparsecs, 10 megaparsecs. Those astronomers in the audience will know that if you're sampling the universe without a redshift, without some redshift indicator, you get isotropy, and then finally you start hinting anisotropies at 100 megaparsecs, and definitely anisotropic at 10 megaparsecs. So if you really want to see the first sources, you want to measure here and not there. Because when you are at 10 to the 18, you see everybody together, and that's isotropic, right? So, it's like trying to understand what galaxies are by looking at a plot like that. That's a bit tough. So you start with the local galaxies before you get to everybody else's galaxies. So the situation is hints at 60 eV, but really dominated by a background, so even if you see some sort of deviations at 3 sigma from isotropy, you still don't really have a good measurement, a 5 sigma measurement. Here's just one latest update from the telescope array that connects to the SwiftPath catalog, showing an interesting P, meaning that there is interesting correlations there, but not a 5 sigma signal again. So the bottom line is because there are hints, and if we really want to solve the question, we need a significant increase in statistics above 60 eV. And that's what we call extreme energy cosmic rays. It's above this threshold when things should be interesting. So here's, for example, one plot of the number for different models. So from iron, mixed iron, and lots of other possibilities that fit all the data we have today, you get that the number of possible sources contributing at 40 eV is much higher than 20 for all the models. As you go to higher and higher energy, so 70, 80 eV, you end up with 4 sources in the sky. So that's the goal, is to get 4 sources or less in the sky. And here, 2 options. If you get 1,000 events above 60 eV or 100 events above 100 eV, you do both at the same time with the same kind of exposure, you definitely can identify a proton-rich type of situation. What are the 4 nearby sources? If you even have a very mixed composition, very much proton poor, you can identify some of these sources also when you get to these numbers. Okay, so 1,000, and this is just another measurement for why 1,000 is important. A 5 sigma discovery requires 1,000. So everybody agrees that if you get 1,000 events above 60 eV, you start doing, you should be able to nail the source. Okay, so how do we do that? We get a lot more data above 60 eV over the whole sky. That's the goal. Auger and TA, to put together, they see 30 events per year above 60 eV. Is that I should shut up? Is that kind of? All right, almost there. All right, 30 plus years to get to 1,000. We're just going to do some algebra for fun, and we'll finish up. And the Earth's surface is a lot bigger than that. So we have, this is my point, okay? So we have 5 orders of magnitude to grow in numbers of events above 60 eV. We just have to be very bold. And to be very bold means that we want to monitor a lot more of the atmosphere than what we can do by sitting on Earth. So let's go to space and look down on the atmosphere. I think that's my biggest point, which is that if you go and you monitor the atmosphere by flying around the Earth, for example, in the JMUSO project, you can get, my phone seems to, 200 events above 60 eV, okay? So we can knock 1 order of magnitude out by putting something in space, and here's what JMUSO stands for. 2 more transparencies. One is to tell you what the acronym is for. It's the Extreme Universe Space Observatory, called UZO, in the Japanese experiment module, JAM, at the International Space Station, okay? So this is a big collaboration which is trying to get together and build a payload that would be then housed next to Calette and Ice Cream in the Kibo mode at the ISS. And therefore, by looking down from here, you can see the whole sky, because the International Space Station goes around every hour and a half. And you can pioneer the study of the extreme energy cosmic rays from space, increase the exposure of the extreme energy cosmic ray by 1 order of magnitude and discover the nearby sources of ultra-high energy cosmic rays. Thank you.